temperature at outlet drain for hot water, and this shows the value of temperature at cold water for outlet. Okay. Okay. The constant, we are constant at hot water volumetric flow rate at 0.66 meter cubic per hour. So we are manipulating the flow rate of volumetric flow rate of cold water. Okay, first we are manipulating at 1.5 meter cubic per hour, and then after we get steady state, and then we adjusting the flow rate to 1.7 meter cubic per hour. Okay, that's all.
The alarm is beeping, so we know that we have some error. So we put acknowledge, and then we open the glass flow. Then we see at this level is so low. So we open the valve so that the flow will be higher again. They estimated the good part, the good level should be here. Yeah. The flow is going higher and higher. So within this range, it should be good. So we close the valve again. Okay, that's all.
Now we will show you how to get our transfer function. Right here, we are from our data, which is temperature. This one ABS. Okay, temperature absolute. We will change it to deviation temperature, which is the temperature absolute minus with temperature steady state. Okay, temperature steady state is 35.6. Okay, then we get the data. Next, from that we will do a linear regression by finding a t bar, and using linear regression we use error squared negative error squared, sorry. Then the total up of error squared, we will approach to 0. We will approach to 0. This one we will approach to 0. Then from that data, we plot the graph. Then the t bar will be approached to our data from experiment. Then we get our k value, theta and tau. Here is our k value, theta and tau. Then we use direct substitution method, and from this GP, we use the characteristic equation, and then we plug in this GP into this characteristic equation. Okay, for this characteristic equation, for GP we use this GP, and then GC we use PI. Okay, and then this time delay, we substitute Euler method. This cos 4.4 omega minus g sine 4.4 omega, and then we expand it until we get this equation, which is this one is the final. We separate the real and imaginary. From this equation we find the KCM. We use an Excel, which is we use a solver by set this imaginary to 0 by changing omega, and then we get this KCM and set the tau to 10. And for the block diagram, okay, this is our block diagram. This is the gain is 0.0672 as we get in the Excel when using the solver, and this is our transfer function, transfer our GP, and our transport delay. So the graph that we get. Okay, so this is what we get. It shows that the graph is stable. Okay, we do Ziegler method, Cohen-Kuhn, and IMC, and ET. Okay, for Ziegler, we use this formula KKC T1 over tau, tau D over tau. And this is our GP that we get from the K, the tau, and the theta we get from the linear regression. Okay, so this is how our transfer function, PID controller, and transport delay looks like. So after we calculate this KC, the tau 1 and tau I and tau D, we we keep in PID controller, and yeah, this is our transfer delay, and the transport delay is 4.4. And this is for CC, Cohen-Kuhn. Same goes with Ziegler. We get the value of KC, tau I, and tau D. Then this is tau D. Okay, and then we keep in the PID controller. This one. And the transport delay. Okay, so this is our transport delay that we keep in the Simulink 4.4. So that's all. Continue with Imran.
Has explained about Ziegler-Nichols and Cohen-Kuhn. Okay, I will explain about IMC and ET method. Okay, how we get our KC, our tau I and tau D from the IMC is by using the formula in the books. This is the H table from the IMC table. So we get that our KC will be this one, our tau I will be this one, and tau D will be this one. So from that we can calculate P, D, and I. So after we done calculating the PID, we substitute into our Simulink in the PID controller. As you can see, Farhan akan click it. We get our PID value from the calculation. We key in into our PID controller in the Simulink, and then we click OK. After that, the time delay should be 4.4. It is 4.4, and then OK too. After that, we calculate the ET method. The ET method, we also calculate the KC, the tau I, and the tau D. So from the formula in the book, we managed to get the KC value, this one, and the tau I value is this one, tau D, this one. So we calculate the PID from this information, and we also substitute into this PID controller. This you can see PID controller ET differentiate. Okay, the value is a bit different from the IMC, and okay, uh, and then the transport delay will be 4.4. It is same all over the method. From the PID controller that we substituted the value, we managed to get 4 graphs based on the 4 method. So I will explain about the each of the graph. The yellow one will be the IMC graph. The purple one would be the ET graph, and the blue one would be the Ziegler-Nichols graph, and lastly the red one will be the Cohen-Kuhn. Okay, from this table, we managed to prove that IMC is the most stable among all the method, and the second stable will be the ET, and the third will be the ZN, and the least stable among all the 4 method will be the Cohen-Kuhn, as you can see at the graph.
Hello, Assalamualaikum. Assalamualaikum. So for the next thing, I will show how to plot a body plot from the MATLAB. So firstly, based on the command window, we will input the coding A equal to transfer function, which is TF, and then 31.7881 bracket, which shows the tau, which is 4.1385, and then put some space 1 and put square bracket, and then uh, put input delay, which is 4.4, which is equal to theta. So it will show, so the command window will show like this, which is similar to our transfer function. Exponent negative 4.4 as indicate our time delay. So next, and then we will type OPTS equal to body options. Scroll down. So the coding will be like this. Okay, next we input OPTS dot mac units equal to phosphorus ABS and phosphorus, and then it will equal like this. Okay. And lastly, to plot the body plot, we input this one, body plot bracket A comma OPTS comma, and then grid on axis to so that the x-axis will have a scale of 0.01, 100, negative 200, and 0. So based on our coding just now, so the figure 1 will shows the body plot diagram. So this consists, body plot diagram consists of two graphs. So for the first graph, it shows the frequency at x-axis and phase at the y-axis, and for the second graph, it shows magnitude at the y-axis. So how to read KCU from this graph? Firstly, we read from 180 and we make a straight line, okay, from the curve which intercept to the 180 line, and then we make a vertical straight line and intercept with this curve. So from this we read at the y value, which shows the magnitude of 14.5. So from that, from the formula, KCU equal to 1 over 14.5, we Alright, next we will proceed to the online tuning, where we will manipulate our KC here. Alright, by manipulating this, we will manipulate our KC until it this oscillation, the amplitude almost the same. Okay, if when the amplitude is almost the same, our KC will be our KCU. Right, next, okay, this one is our what is our KCU is what is KCM when the amplitude is same. Alright, next, from this graph, we take from this one to this line to get one oscillation. So that one we call as PU, period ultimate. Right, next, we use the value of KCU and PU. We include in our table 12.7 in our book textbook. Alright, from that, we will calculate a new PID controller. Alright, so the value of PI, the value of I and D is substitute in this column. Right, so we remain our GP and we remain our transport delay, which is 4.4, and we will view it in our scope. From the value we get this graph.